This week, we are going to complete the subjects in this course. And the last subject we are going to discuss is graphs and trees. Of course, probably you all know that this actually warrants an entire course to itself. So what we are going to do here is just give a brief introduction, uh, define some key concepts, and talk about some uh, important problems in graph theory, and give some algorithms that are essential and describe some structures. So the list of subjects we are going to talk about is listed here. You see, it's quite an extensive list because this is a huge subject, in fact. However, as I said, we are going to be quite brief about it. So we are going to start with definition of the concept of a graph and their representations. And we will talk about weighted graphs, then the problem of graph isomorphism. Then we will talk about paths, circuits, and connectivity of graphs. And in this context, we are going to describe Dijkstra's shortest path algorithm. We will define planar graphs and its relation to graph coloring problem. And we will give some algorithms for graph traversing. Then we will move on to trees. We'll define what a tree is as a structure, and we will consider special types of trees. And one of the most important structures is binary search trees. And then we will talk about some algorithms for tree traversal, and we will finish with spanning trees and minimum spanning trees. So in general, we are going to talk about graphs and trees as mathematical structures, but also we are going to see them as data structures that we can use in building software. So this is sort of a dual, let's say, perspective. In general, we are going to stay in mathematical context, but we will also talk about certain algorithmic aspects. Okay, to begin with, let's define what a graph is. Essentially, a graph is a structure consisting of a set of vertices, which we also call nodes, denoted by V. And this set cannot be empty, so we need at least one vertex. And we also have a set of edges, denoted with E, that connect some of these vertices. And we have a number of types of graphs. The most simple one is, as the name implies, the simple graphs. The simple graph here, we allow only one edge connecting a pair of vertices. So we do not allow multiple edges between vertices. And also we do not allow loops, these edges connecting a vertex to itself. And finally, edges are undirected. So in a simple graph, you don't have multiple edges between vertices, you do not have loops, also you do not have directions on the edges. In contrast, in a multigraph, we allow multiple edges, and depending on your definition, some people allow loops and some do not in a multigraph. So if you allow them, of course, you will allow multiple loops at a vertex such as this one, and vertex number 3 having 2 loops here, 2 edges connecting to itself. But some resources you might see also disallow loops in a multigraph. But still, we have undirected edges in a multigraph. The next definition, we have a digraph or a directed graph. As the name suggests here, the difference is that we have directions on each edge. And therefore, for instance, consider this example here. You have an edge connecting 1 to 3 in that order, 1, 2, 3, this one. And at the same time, you also have another edge connecting 3 to 1, this one. Okay. So here we allowed loops and multiple edges in the most general context. For instance, you have 2 edges from 2 to 1. So where do we use these structures? So where do we use graphs? And later on we will see trees. Where do we use them? What to represent with graphs? Networks and topologies. These could be real physical networks like communication networks or computer networks, or it could be, let's say, a network of relationships, for instance, between people, or between, let's say, social media accounts, or between, for instance, people that are affected from an epidemic, for instance. There are mathematical models that use graphs to represent uh, the relationships between people in that aspect. Obviously, I've talked about communications, software and task dependency. So which task affects which one, or which task needs to be done before the other task. In other words, precedence. Airline or traffic. This could be like motorway traffic, or any other traffic you can think of. For instance, traffic in production lines in a factory can also be modeled using graphs. Biology and ecology models, like which species prey on which species, or which species use what materials, etc. So you can use graphs to model these types of relationships. Chemical compounds obviously can be modeled as graphs, or for instance, printed circuit boards can be represented using graphs, and we will mention some examples where some theoretical problems relate to real life scenarios, for instance, in printed circuit boards.